Today we're going to talk about solving exponential equations. We're going to have two methods of solving. For our first method, what we're going to do is try to equate or make equal our exponents. And the way that we can do that is if the bases are also the same. So if we have an exponential on both sides of the equal sign, and they have the same base, then the exponents must also be equal, because an equal sign acts like a scale, and whatever is on one side should exactly match the other side. So if the bases exactly match, then the exponents should exactly match. So that's the first method we're going to use. So what we want to do is, on both sides, look at what the bases are. So on one side we have a base of 4, on one side we have a base of 8, and those are not equal to each other. Our goal is to see, if possible, if they can be made to be the same by powers, because we're talking about exponential equations here, so we want to use exponents or powers. So 4 and 8 are both powers of 2. So I can write 4 as 2 squared, and I can write 8 as 2 cubed. So we're going to change the bases so that they are both the same. Now they are both bases of 2. And if the bases are the same, then the exponents must also be equal to each other, because 2 to something has to equal 2 to that same thing. It can't equal 2 to anything other than what it was already equal to. So then we can ignore the bases and just set equal the exponents. Now on the left-hand side, we have up in the exponent a 2 and a 3x. What do we need to do with those? Multiply them, because it's a power to a power. So we're going to multiply that. We're ignoring the base, but now up in the exponent, that 2, we're going to multiply by the 3x to make 6x. And likewise on the other side, we can ignore the base. We need to multiply that exponent, but we need to distribute here. So 3x plus 3. And we solve by subtracting 3x. And dividing gives x is 1. One of the really nice things about solving an equation is the algebra is you can always know if your answer is at least right or wrong. You don't always know how to fix the mistake if it's wrong, but you can always at least know whether your answer is right or wrong by taking it and plugging back into the original equation. So if I plug in a 1, I would get 4 to the third is equal to 8 squared, and we could confirm by plugging that into our calculator that those are the same. They are both 64, so this works. Mm-hmm. Yep, x equals 1 is the solution to that one. And this one on the left, I have a base of 2. On the right, I have a base of 32. Those are not the same, so then our question is, can they be the same? Can they be written with the same base? Well, there's no way to break down a 2, so then the question is, can we write 32 as 2 to the something? We can, but what? 2 to the 5th. Feel free to use a calculator to guess and check on those to get to the right power if you need to. If you play 2048, you might be better with your powers of 2. You see them in that game. But 2 to the 5th is 32. So now the bases are the same, which if the bases are the same, that means the exponents must also be the same. So I can ignore the 2 and say 4x must equal, ignore the 2, distribute 5x minus 5. So subtract 5x from both sides. We get negative x is equal to negative 5. So x must be 5. Again, you don't have to, but you can always check your answer by plugging it back in. If I plug in a 5, I would get 2 to the 20th and 32 to the 4th. Now I have no idea what those are, but you could grab a calculator and plug them in and confirm that you do in fact get the same answer for both of those. Questions? Go ahead and try this third example. Okay, there are two different ways to solve this problem. 9 and 81 are not the same right now. What could I write them as to make them be the same? I could leave them as 9, and then we could have a 9, and an 81 is a 9 squared.
You got 10.
And then we saw the 3x minus 2. Did anybody use a different base other than 9?
I did 3 squared.
3. Yep, 3 works as well. So we could do 9 is 3 squared to the 2x, and then 81 is 3 to the 4th, and then the 3x minus 2.
What?
Both work, right? Because both are true. So we can either leave the 9 a 9 and make the 81 a 9 squared, or we could change both the 9 and 81 into powers of 3, because they are. It doesn't matter, you will get the same solution either way, because 3 squared is 9 and 3 to the 4th is 81, so it all works out either way.
Is one easier to do than the other?
No, it's just kind of whichever one you see. So if you see powers of 9 or if you see powers of 3, it doesn't really make any difference in the solving. I'm going to go ahead and just work out the first one here. So I would ignore the 9 and say 2x is equal to, ignore the 9 and distribute 6x minus 4. I'm going to subtract 6x from both sides. That gives negative 4x equals negative 4, which gives x equals 1. And if we take that back, we would get 9 squared is equal to 81 to the first, which is true. 9 squared is 81, 81 to the first is 81. So it works out. You should get that same exact solution even if you use the base of 3. Questions on this method? This method is great when it works. It doesn't always work though, because you can't write every 2 numbers as a power of some other number. So this method will not always work, which means we need a second method. So our second method is we're going to undo the exponentials by taking logs. Okay? Whenever we're trying to solve an equation, we need to undo what's being done to the variable. So if we have multiplying in our equation, we undo it by dividing. If we have adding in our equation, we undo it by subtracting. If we have squaring, we undo it by taking square roots. So if we have exponentials, the way we undo an exponential is with a logarithm. And we could either use a common log or we could use a natural log. It doesn't matter. They both work. Sometimes one may be preferable to the other, and I'll show you about the special cases there. Our steps are that we need to get the exponential part alone. We cannot have anything added to it, and we cannot have anything multiplied by it. We need to get the exponential totally alone. Then we're going to take some kind of a log of both sides, either a common log or a natural log, and then we'll proceed solving for x. So the first thing I always check is, can I write them as the same base? So 2 to the x, can I write 7 as a power of 2? And I can't. 8 is a power of 2, but 7 is not. So we can't do this one with our first method. So then our first step is get the exponential alone. It is. It's just 2 to the x. There's nothing else happening over there. There's no adding. There's no multiplying. It's just 2 to the x. So it is alone. Our second step then is to take some sort of a log of both sides of the equation. It doesn't matter which one. So I'm going to take a natural log because then I only have to write 2 letters instead of 3. Seriously, I'm that lazy. Then we're going to apply a property of logs to this. So in the last lesson, we learned some properties of logs. What do we do with a power inside of a log? We drop it down out front as a multiplier. So this is now x times the ln of 2 equals the ln of 7. And then how do I undo the timesing? Divide by the ln of 2. And our answer is going to be the ln of 7 divided by the ln of 2. And you just throw that in a calculator and get 2.8. In this one, our exponential is not alone. So our first step is that we need to get the exponential alone, and we need to do that by subtracting 4 from both sides. Your exponential must be alone if there's anything multiplied on that side or added to that side or subtracted or whatever it may be, that you need to get rid of it first. So we need to get rid of that 4, subtracting it from both sides. Now we cannot write 17 as a power of 10, so we can't use our first method on this. So then we need to solve this with logarithms. This is a case where it really still does not matter which one you do, a natural log or a common log, but it is easier in this problem to do a common log. Why do you think that might be? Why do you think the common log would be preferable in this problem? Because there's a 10. So the common log has a base of 10, and this problem already has a base of 10 happening in it, so that will simplify our work in this problem. So I tend to do a natural log unless I see that 10 in there, and I'm going to do a common log this time. Because what happens when the base of our log matches the base of our exponent? They cancel each other out. So that whole stuff over there disappears, and all we're left with is 2x minus 3 equals the log of 17.
Wait, where'd you get 2x minus 3 from?
That's
Oh,
of the
okay.
exponent. Now we need to get x alone. So I'm going to do that by adding 3. When you add 3, you cannot add it to the 17. That 17 is inside of the log. It already has something being done to it, so we can't do more to it. Okay, so we need to add 3 just to the whole thing, not to the 17. And then we need to divide by 2, again, to the whole thing, not to any part of it. So then in the calculator, we would type log, it opens parentheses, do 17, close them off, plus 3, hit enter, and then divide it by 2, hit enter to get your answer. And I have a wrong answer on my sheet, so I don't know what the right answer is. Let's see. Log of 17 plus 3 divided by 2. 2.1. Questions? On this one, our exponential is totally alone already. It's just a 4 to the x. There's nothing else happening on that side. Can we write 15 as a power of 4? No, we could write 16, so it's really close, but not quite. So we need to solve this with logs. It does not matter on this one whether we take a common log or a natural log. So I'm going to take a natural log. Take the x and drop it down. It's now x times the ln of 4. So to undo times,
Last call.
we divide.
Good. It'll
Thank
be in
you.
the office. Or you on the edge.
Thank you.
And then we type into the calculator the ln of 15 divided by ln of 4. Again, when we were doing our change of base formula, we were typing in things like this, and it is very important that you close those parentheses. You get 1.95. Which in checking the plausibility of our answer, that's pretty close to 2, but a little bit smaller. So if I plugged into 4 squared would be 16, but a little bit smaller. So that makes sense for an answer then.
Wait, how come you didn't use log?
You could use a log if you wanted. It doesn't matter. I typically tend towards ln unless I have a base of 10 in the problem.
Okay.
But it really doesn't matter. If you did a log on this problem, it would work exactly the same.
Okay.
Go ahead and try this one. On this one, our exponential is totally alone. It's already just 5 to the x. There's nothing added. There's nothing multiplied over there. So we can begin by taking a common log or a natural log. It does not matter which. Powers drop down as multipliers. So it is x times the ln of 5 equals the ln of 18. X times something, we undo times with divide. So then in our calculator, we divide the natural log of 18 by the natural log of 5, or if you did common logs, that's totally fine as well. And we get about 1.8. Again, to check the plausibility of our answer, this is like 2 but a little bit smaller. So if I plugged in a 2 to the original equation, 5 squared would be 25, but I want it to be smaller, so 18. But you could actually just check it as well by typing into the calculator 5 to the 1.8, and you should get something pretty close to 18. Make sure you're closing your parentheses after the 18. On this one, our exponential is not alone. It has a 3 added to it. So I'm going to begin by subtracting 3 from both sides. Now the exponential is alone. We cannot write 22 as a power of 5, so we need to solve this with logs. Because 5 is not a special number as a base, we could use a common log or a natural log, and it does not matter which, so I'll use the natural log. We're going to take the x plus 2, the power, and drop it down front as a multiplier. To undo multiplication, we divide. But x is still not totally alone, so I need to subtract 2. And this is what we type into the calculator, making sure you close the parentheses after the 22 and after the 5. After the division.
So should you press enter first, or does it matter?
It doesn't really matter as long as you close the parentheses after the 5, or you could press enter. It doesn't really matter. Did I get about negative 0.08 or negative 0.1? To check that as a plausible answer, that's really close to 0. So if I plugged in 0, I would have 5 squared, which is 25, plus 3 is 28. It's a little bit too big, and our answer is actually a little bit smaller than 0. So that makes sense. In our last example here, the exponential is not alone. We have that 8 with it, so we need to begin by getting rid of the 8, subtracting 8 from both sides. Now the exponential is alone, and the exponential has a special base. It has a base of 10, which means on this problem, I am going to choose to take the common log, the log of base 10. Because log base 10 of 10 will cancel out and leave me with just the 5x plus 4. Then to get the x alone, I need to subtract 4. Again, we are not subtracting from the 27. We are subtracting from the whole side. And divide by 5. Again, we're dividing that whole side by 5, so this is where on the calculator you would want to do your log of 27. Make sure you close those parentheses, minus 4, enter. Divide by 5, enter, since it's dividing the whole thing by 5. We should get about negative 1/2. I want to do one more example with a special base. So let's say I have 2e to the x plus 1 minus 4 equals 10. What do I need to do first here?
Plus 4.
Add 4. What do I need to do next?
Put x plus 1 on the outside.
Not yet.
Divided by 2.
Divide by 2. We have a multiplier on this one. Your exponential needs to be totally alone, so it's just base and exponent, nothing added, subtracted, multiplied, divided. So we need to get rid of that 2 as well. Now we can not yet drop this stuff down until we have some sort of a log here. What kind of a log would we want to take on this one? A natural log. Typically it doesn't matter, but if I see a base of 10, I do a common log. If I see a base of e, I'm definitely going to do a natural log, and otherwise you do whichever one you like best. But a natural log with a base e of e will leave us with just an x plus 1 equals the ln of 7.
Minus 1.
Subtract 1 and make sure you're subtracting 1 from the whole thing, not from the 7. So close off the parentheses when you type it in the calculator. Okay? Where it says the first 5 you can equate exponents, that means the first 5 you can use the first method we learned where you make the bases the same and set the exponents equal to each other. The remainder of the problems you will need to solve with logarithms.